Okay, everybody. It's time for discussion 7.2, polarity and intermolecular forces. So what does it mean to be polar? Polarity refers to any structure that has oppositely charged ends. Right, so this magnet shows it's got north, which is positive, and south, which is negative. Right? So if there are not charges on the end of the structure, then we call it nonpolar. Now you'll notice we say oppositely partially charged ends. Right? So in ions we have full positive and negative charges, but in a molecule it doesn't work that way. They're only partial positive and partial negative. So we represent partial charges with a lowercase delta. It's kind of like a fancy looking D. And for partial positive, we say it's delta plus, and for partial negative, we say it's delta minus. Now we're going to look at two types of polarity here. We're going to look at whether or not bonds can be polar or nonpolar. And we're also going to look at whether or not molecules can be polar or nonpolar. So let's start with bonds. Now, you have to recall that covalent bonds are created when two atoms share a pair of electrons. So here in our water molecule, we have the bond between hydrogen and oxygen consisting of one electron from hydrogen and one electron from oxygen. All right, so we can determine whether a bond is polar or not by looking at the difference in the electronegativity values between the two bonded atoms. Now we'll talk about that a little more on the next slide. If a bond is nonpolar, the electrons will be shared equally between the two atoms. Right? Now this means if they're shared equally, the difference in their electronegativity is 0. That means the two atoms will have the same value for electronegativity. And a polar bond will occur when the electrons are shared unequally. That means there'll be more electrons on one side of the bond than the other. And that is what creates that partial positive and negative charge. Now, a polar bond has what is known as a dipole moment. Kind of a strange word. And a dipole moment is indicated with a vector arrow. So it's an arrow with a little tail at the end. And the dipole moment arrow will always point toward the negative. So what is the role of electronegativity? So electronegativity is an atom's ability to attract electrons to itself. So I like to think of the sharing of electrons in a covalent bond as like a tug of war. Now, since electronegativity is the ability to attract electrons to yourself, the more electronegative atom will have a greater share of the electrons. It'll be winning that tug of war. This will make its side of the bond partially negative, and that's because electrons are negatively charged, and so wherever the electrons are, that will be the negative side of the bond. So let's look at an example between hydrogen and chlorine. So first of all, hydrogen has an electronegativity value of 2.2, and chlorine has an electronegativity value of 3.2. Because that does not equal 0, we know that this is a polar bond. Right? Now, since chlorine has the higher electronegativity, the dipole moment will be shown pointing toward chlorine, which will make this side of the bond partially negative and this side of the bond partially positive. So different elements, for the most part, will have different electronegativity values as far as you're concerned for this course. So if the bonded atoms are different, then you can go ahead and assume that the bond is polar. If the atoms are the same, like let's say it's two bromine atoms, since both bromine atoms have the same electronegativity, the difference between those values will be 0, and that would be a nonpolar bond. So let's go ahead and sum up. We've got nonpolar bonds and polar bonds. In a nonpolar bond, the difference between the electronegativities will be 0, and in polar covalent, it'll be some value greater than 0. The sharing of electrons in nonpolar is equal, so there's no advantage in the tug of war. In a polar bond, the sharing of electrons will be unequal. because you have one element with a greater electronegativity. You can recognize a nonpolar bond because it'll be the same atoms. And you can recognize a polar bond because the atoms will be different. Now, I just want to note, in actuality, all the elements of the periodic table are splitting electronegativity values from like 1 to 4. So some atoms will have the same electronegativity, but you are not going to encounter that in this course. So if the two atoms are the same in the bond, then it's nonpolar, and if the two atoms are different, then the bond is polar. All right, so now let's talk about the polarity of molecules. All right, so molecules, like bonds, can also be polar or nonpolar, and a molecule will be considered nonpolar if there is no net overall, that should be an I, dipole moment. What that means is that molecules that have polar bonds can be nonpolar overall. So we have our example up here. This is carbon dioxide. Carbon dioxide has two carbon-oxygen bonds, both of which are polar. Now, oxygen has the greater electronegativity, and so the dipole moments in both cases will point toward oxygen. But since they are equal and opposite, they cancel each other out, and there is no net dipole, so carbon dioxide would be nonpolar. Water, on the other hand, has two dipole moments, both pointing toward each other, so the net dipole moment is represented by that blue arrow. Since all the dipole moments don't cancel out, we can say that that molecule is polar. Now, that's why or how molecules are polar or nonpolar. But in this course, all you really have to do is recognize whether they're polar or nonpolar, and you don't have to explain it. So you can tell if a molecule is polar or nonpolar simply by looking at its shape. There are three shapes that will almost always produce nonpolar compounds. You'll see that a couple conditions need to be met. And there's two shapes that will always be polar just about no matter what. So the three nonpolar shapes are linear, and linear looks something like this. The second is trigonal planar, which looks somewhat like this. Sorry, this is kind of a crappy drawing. And the third is tetrahedral, which looks kind of like that. All right, and the two polar shapes are bent and trigonal pyramidal. So bent will often look like this, and pyramidal looks like that. So you can see all the nonpolar shapes if you look at the diagrams. None of the molecules have lone pairs on the central atom. And in the two polar shapes, both of the examples have lone pairs on the central atom. And that becomes key. Because if there are lone pairs of electrons on the central atom, then that tells you right then and there that the molecule is polar. Now, this isn't always true, but for the purposes of your course, if there's lone pairs on the central atom, the molecule is polar. Now, nonpolar shapes will only be nonpolar if one important condition is met. And that condition is that all of the atoms on the outside are the same. So whenever you're looking at a shape, you have to ask yourself, are there lone pairs on the central atom? If the answer is no, the molecule will be nonpolar only if all the atoms on the outside are the same. So if I look at CH4, which is methane, there's no lone pair on the central atom, and all the outside atoms are the same. So this is a non-polar molecule. In this example, this is chloromethane. There's no lone pair, so that condition is met. But we have 3 atoms of hydrogen and 1 atom of chlorine. So all of the atoms on the outside are not the same. That means this molecule is polar. All right, so I want you to take a moment and practice. We got a couple bonds and a couple molecules. I want you to tell me whether these are polar or nonpolar. Go for it. Okay, so here we have a bromine molecule. This is a bond between 2 atoms. The atoms are the same, so the molecule is nonpolar. Here's HCl. This is also a bond. The atoms are different, so this bond is polar. And the dipole would look like that. Here we see no lone pairs of electrons on boron, and the atoms on the outside are the same, so this molecule is nonpolar. If I replaced one of those F's with something else, then it would be polar. Oh, we have a lone pair of electrons on the central atom. No more questions need to be asked. It's polar. Same thing here, lone pairs of electrons, so this is also polar. Now here, the last example, fluoromethane, I do not see any lone pairs of electrons on the central atom, but I have 3 hydrogens and 1 fluorine, so all the atoms on the outside are not the same, so this molecule is polar. Okay, so let's talk about intermolecular forces. Now let's break apart this word intermolecular. Inter means between, just like interstate highway, and molecular obviously refers to molecules. So intermolecular forces are the forces of attraction between molecules. Right, so here we have 3 molecules of HCl. Right? Now, the space between the molecules is where the intermolecular force is. If we want to talk about the actual bonds of the molecule, we would call those intramolecular because they are inside the molecule. Right? So intermolecular forces are the forces that hold molecules together. So there are 3 types of intermolecular forces, which are often abbreviated IMF. The type of IMF between certain molecules can be determined by the polarity and bonding of the molecule. So there's of the 3 types of IMFs, the first is dispersion forces. Now dispersion forces are the only intermolecular force in nonpolar molecules. So if your molecule is nonpolar, the strongest intermolecular force is dispersion. Now the next is dipole-dipole interaction. And dipole-dipole will occur in polar molecules. Now, this designation dipole-dipole, the reason they repeat the words is because the nature of this bonding, this intermolecular force, is polar molecules lining up with opposite ends close to each other. So positive lines up with negative. And that space in between is the intermolecular force. Now, next is hydrogen bonding. Now, hydrogen bonding is actually a type of dipole-dipole force. All right, but a special condition must be met. Hydrogen bonding, will only occur in molecules that have atoms of hydrogen bonded to nitrogen, oxygen, or fluorine. So if you're asked to identify the strongest intermolecular force in a compound, you have to look at the bonding as well, because if it's polar, it could have dipole-dipole as its strongest, or hydrogen bonding if it contains one of these bonds. So some classic examples of compounds with hydrogen bonding are water. We know water is polar because of the lone pairs on oxygen, and we have oxygen atoms bonded to hydrogen, so we have hydrogen bonding. Another would be hydrogen fluoride, also polar because it's not the same atom in the bond. And we have fluorine and hydrogen bonded together, so that gives us hydrogen bonding. The last example would be ammonia, which is NH3. Again, we know that this is a polar molecule because of the lone pair of electrons on nitrogen. And since nitrogen atoms are bonded to hydrogen, we can say that it has hydrogen bonding as its strongest intermolecular force. Excuse me, I just had lunch. All right, so here's just a diagram showing a hydrogen bond. So here we have two water molecules. Notice the oxygen end of the water molecule is negative, and the hydrogen ends of the water molecules are positive. So in the hydrogen bond, the positive end of one water molecule lines up with the negative end of another, and that bond in between, the space in between the two water molecules, is the hydrogen bond. All right, so the strengths of IMF, all three types have different strengths. If we go on a continuum from weakest to strongest, we see that dispersion forces are very, very weak. Dipole are in the middle, and hydrogen bonding is the strongest. Now, this is important because the IMF type in a molecule will determine several of its physical properties. All right, so for I have two for the next two slides to practice. I want you to determine whether each molecule is polar or nonpolar and identify the strongest intermolecular force. So pause the video and go ahead and do that. Okay, here we have methane again. We don't see any lone pairs of electrons on the central atom. All the atoms on the outside are the same. So this molecule is nonpolar, and nonpolar molecules only have dispersion forces. The next example, chloromethane. We know that this is polar because all the atoms on the outside are not the same. So we have to ask ourselves, does it have dipole or hydrogen bonding? Well, we have atoms of hydrogen in the molecule, but none of them are bonded to nitrogen, oxygen, or fluorine. So the strongest intermolecular force is dipole-dipole. Finally, when you're looking at a molecule, one thing you want to look for is symmetry. Right? We want to look for symmetry in the XY plane. Right? Because if the molecule is asymmetrical, then you're going to have an asymmetrical distribution of charge. So oxygen, we know, is very electronegative. It's the second most electronegative element on the periodic table. So it is going to draw electron density toward itself, making this a polar molecule with a negative end down here and a partially positive end over here. So because this molecule is polar, we have to choose between H bonds and dipole-dipole. Since we have oxygen bonded to hydrogen, we can say that the strongest intermolecular force is hydrogen bonding. All right, now for these next examples, same thing here. We have oxygens over here, so that's going to make partial negative and partial positive. That means this is a polar molecule. I'm just going to write P to save time. And we have oxygen bonded to hydrogen, so the IMF is H bond. Here we have the bromine molecule. This is nonpolar, as we know. It's a bond. The atoms are the same, so the strongest intermolecular force is dispersion. And finally, we have HCl. We've looked at this several times already. That's a polar bond. We have hydrogen, but it's not bonded to nitrogen, oxygen, or fluorine, so the strongest IMF is dipole-dipole. All right, so let's look at the effect on physical properties. So boiling or evaporation, and to a lesser extent melting, are the separation of molecules. Right, if we turn something from a liquid to a gas, those molecules are spreading out when they turn to the gaseous phase. So stronger intermolecular forces will mean the substance has a higher boiling and higher melting point. I have to change that. Now, again, because boiling is separating, the stronger or the harder, tighter those molecules are held together, the more energy will need to be put into them in order to make them boil or melt. Now, stronger intermolecular forces also mean a higher surface tension. If you don't know what that means, the definition is right down here. Now, it says higher volatility. What I meant to say down here is lower volatility. Now, volatility is the ability of a liquid to evaporate. So if the boiling point is high, that means the volatility is lower. And they'll also have higher viscosity. And viscosity is essentially just the thickness of a liquid. So weaker intermolecular forces, just things with dispersion forces, tend to have low boiling points, low melting points, low surface tension, high volatility, and low viscosity. So let's just talk quickly about vapor pressure. So liquids, if you leave them out, will naturally evaporate. Now, if you take that evaporating liquid and put it in a closed container, the vapors will build up in the bottle and exert pressure on the inside of the bottle. There'll be a little bit of pressure in there. Now, you can see this pressure when you open up a bottle of soda. You hear that effervescence, and you hear the gas escaping. That's because the gas inside is under pressure. So when a certain pressure is established in the container, evaporation will essentially stop. Now, it doesn't really stop. You form an equilibrium, but we'll talk about that when we get to Unit 9. I don't want to get ahead of ourselves. And each liquid will have its own unique vapor pressure that at the same temperature will always be the same for that liquid. All right? Now, that pressure in the container, in that state, when the pressure is constant, is known as the vapor pressure. And vapor pressure is related to volatility. All right? So the stronger the intermolecular forces, the higher the boiling point is. And the higher the boiling point, the less a liquid will evaporate because it's less volatile. And the less the liquid evaporates, the fewer particles of gas will be in the closed container above the liquid, so the lower the vapor pressure is. So just to sum up, things that have low vapor pressure, this end of the continuum, have strong intermolecular forces. And substances with higher vapor pressure that are more volatile have weak intermolecular forces. All right, so we can see here the more evaporation that occurs. So as we go across here, we're getting less and less evaporation. The more evaporation that occurs, the higher the vapor pressure. And the stronger the intermolecular forces, the less evaporation you will get. All right, and that is it for discussion 7.2. Use this video to study for the test. If you have any questions, please bring them to class. And as always, thank you for watching, and study, study, study. Okay, bye.